Welcome to another video lecture. In this video lecture, we will discuss the time response of a second order system in the underdamping case. Now, in the last class, in the last lecture, we discussed about the time response of a second order system in general with different values of damping ratio. Now, if you can remember, this is the general expression of the transfer function of a second order system, omega n square divided by s square plus 2 zeta omega n s plus omega n square. In this expression, this value zeta is the damping ratio and this omega n is the natural frequency of oscillations. Now, in the last lecture, we discussed that the response of the nature of response of second order system entirely depends on this factor damping ratio. And we discussed different cases of this damping ratio. In the first case, we discussed that if the value of zeta is from 1 to infinity, that means if there is a high value of damping ratio, then this condition is known as overdamping, and we get the nature of the response is exponential. In the second case, we considered zeta is equals to 1, and this condition is known as the critical damping. And in this case also, the response was exponential, but the settling time was low compared to the previous case. In the third case, we discussed that if the value of zeta lies from 0 to 1, then this case is known as the underdamping case, and in this case, the response is damped oscillations. We get oscillations, but the amplitude of the oscillations keep on decreasing. In the fourth and final case, we consider zeta is equals to 1, and this condition is known as the undamped condition, and in this case we get pure oscillations at the output of a control system without any damping. Now, in this video lecture, we will discuss the underdamping case where the value of zeta lies from 0 to 1, and in this condition we will derive the expression for the output response. So let us derive the expression for the second order system in the underdamping case. So we'll start with the transfer function. The transfer function of the second order system is omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now, in this transfer function, this is the characteristic equation, the denominator term. So let me write the characteristic equation s square plus 2 zeta omega n s plus omega n square is equals to 0. So this is the characteristic equation, and we already discussed in the previous class that there are two roots of this characteristic equation, s1 and s2. This is the quadratic equation, so these two roots are minus zeta omega n plus, since we are considering that the value of zeta is less than 1 and greater than 0. So in that case, if you can remember, the value of discriminant will be negative, and we get the complex conjugate roots. So in this case, the roots s1 and s2 is equals to minus zeta omega n plus j omega n 1 minus zeta square, and there are two roots s1 and s2. So the first root is minus zeta omega n plus j omega n 1 minus zeta square root, and the second one is minus zeta omega n minus j omega n square root 1 minus zeta square. So in this equation, let us assume that zeta omega n is equals to alpha, and we already discussed in the previous class that this is the frequency, damped frequency. Omega n 1 minus zeta square is omega d, which is the damped frequency. So in this case, the roots now will be s1 s2 will be minus alpha plus minus j omega d. Okay, so let us now calculate the unit step response of this second order system. So the transfer function now is rs by cs is equals to omega n square s square plus 2 zeta omega n s plus omega n square. Now for the unit step response, the value of rs is 1 by s, since the Laplace transform of ut is 1 by s. Laplace transform of ut is 1 by s, so rs is 1 by s in case of unit step response. So in this case, the response cs will be omega n square. I'm cross multiplying these rs with this equation, so this will be s square plus 2 zeta omega n s plus omega n square. Now, to calculate the response, time response of the second order system, which is ct, which can be determined by taking inverse Laplace by taking inverse Laplace of Cs, or rather I should say Laplace transform Ct is Cs. So in order to get Ct from Cs, we have to take inverse Laplace. So we have to take inverse Laplace of this equation here to calculate the time response of the second order system for underdamping case. Now to calculate the inverse Laplace of Cs, we have to do partial fraction of this equation. So let us assume that the partial fraction of this equation is a by s plus, since this is the second order equation in the denominator, we will do partial fraction according to this rule, bs plus c divided by s square plus 2 zeta omega n s plus omega n square. Now we can easily compare the left hand side and our right hand side to calculate these coefficients a, b and c in the partial fraction. Let me directly write these values. A is equals to 1, b will come out to be minus 1, and c, when you will calculate, it will come out to be minus 2 zeta omega n. So we can put these values in this equation. So finally Cs comes out to be 1 by s, since value of a is 1, and let me take minus common here, and the numerator term will be s plus 2 zeta omega n divided by s square plus 2 zeta omega n s plus omega n square. Now in this equation we have assumed that zeta omega n is alpha, and we have also assumed that omega n multiplied by square root 1 minus zeta square is omega d, natural damped frequency. So let me put these values in this equation. So this will be 1 by s minus s plus, I can write it 2 alpha divided by s square plus 2 alpha into s plus omega n square. Now in this equation I cannot directly calculate the inverse Laplace of Cs until and unless I can make this expression into some standard form. Now to make this into a standard form, I'm adding alpha square and subtracting alpha square in the denominator. So this will now become 1 by s minus s plus 2 alpha divided by, this will become s plus alpha whole square plus omega n square minus alpha square. Now this term omega n square minus alpha square, let me solve this separately here. So this omega n square minus alpha square, so I can write it as omega n square minus alpha is omega zeta omega n, so this will be zeta square omega n square. I can take omega n square common here, so this will be 1 minus zeta square. So I can write it as omega n square root 1 minus zeta square whole square. So this is nothing but omega d square. So in place of omega n square minus alpha square, I can put omega d square. So let me write this expression once again. So this will be 1 by s minus, and I'm separating this s plus 2 alpha into s plus alpha plus alpha divided by s plus alpha whole square plus omega d whole square. Now I know the standard form of the Laplace transform. I know that let me write it separately here. I know that the inverse Laplace of s plus a divided by s plus a whole square plus omega square, the inverse Laplace of this expression is e raised to power minus at cos omega t, and the inverse Laplace of omega divided by s plus a whole square plus omega square, the inverse Laplace of this expression is e raised to power minus at sine omega t. So these are the two standard forms of the Laplace transform. So I have to utilize these two standard forms in order to get the inverse Laplace of this expression. So I'm converting this again to the standard form. So this will be 1 by s minus s plus alpha divided by s plus alpha whole square plus omega d square. So this is standard form, and this remaining alpha, I'm writing this since there is a negative sign outside, so this will be minus alpha divided by s plus alpha whole square plus omega d square. Now still this second term is not the standard form, there is omega in the numerator, so I'm multiplying this with omega d and also divide with the omega d. So let me write it here. So this is divided also with omega d and multiply by omega d in order to make this standard form. Now I can take the inverse Laplace here. So I'm writing Ct is the inverse Laplace of Cs, which is the inverse Laplace of 1 by s minus s plus alpha divided by s plus alpha whole square plus omega d square minus alpha upon omega d into omega d divided by s plus alpha whole square plus omega d square. Now I can take the inverse Laplace of this standard form. So finally Ct is equals to inverse Laplace of 1 by s is 1 minus inverse Laplace of this, again I have already written this standard form, so this will be e raised to power minus alpha t cos omega d into t minus alpha upon omega d into the inverse Laplace of this term. I have again written this here, so this will be e raised to power minus alpha t sine omega d into t. So I hope you understood this till now. Let us further solve this expression. So in this expression, let us take e raised to power minus alpha t common. So we get cos omega d into t plus alpha upon omega d into sine omega d into t. Now let's put this value alpha and omega d here. So this will be 1 minus e raised to power minus alpha. Alpha, again let me put this value alpha, which we have assumed, that is zeta omega n. So let me put this value. So alpha was zeta omega n cos omega d into t plus zeta omega n divided by omega n root square root 1 minus zeta square, which is omega d, and sine omega d into t. Now here omega n will get cancelled. Let take this value outside of this bracket. So this will be 1 minus e raised to power minus zeta omega n. There will be t also, square root 1 minus zeta square. So this will be multiply zeta square cos omega d into t plus zeta times sine omega d into t. So this is our response, time response of the second order system. Now here let us assume a right angle triangle. Here, and let us suppose this angle is theta, the base is zeta, and the hypotenuse is 1. So in this case the perpendicular will be 1 minus zeta square. Now in this right angle triangle, if we will calculate the value of cos theta, let's say the value of cos theta will comes out to be zeta, and the value of sin theta, if you will calculate, will come out to be 1 minus zeta square divided by 1. So this will be 1 minus zeta square square root. So now in this expression we can put this value square root 1 minus zeta square is equal to sin theta, and this value zeta is equals to cos theta, so that we can do some trigonometric calculation, and we can make this expression smaller. So let us substitute these values. So this will be 1 minus e raised to power minus zeta omega n into t divided by 1 minus zeta square, and this value is sin theta into cos omega d t plus this will be cos theta sine omega d into t. Now if you can remember this trigonometric formula, sine a cos b plus cos a sine b, so this will be sine a plus b. So I can write it as a 1 minus e raised to power minus zeta omega n into t divided by 1 minus zeta square, and this will be sine omega dt plus theta. So the final expression for the time response of a second order system in the underdamping case comes out to be this. Now here theta, if you calculate the value of theta from this triangle, this will be tan inverse 1 minus zeta square divided by zeta. So this will be the value of theta here. Okay, so I hope you get this equation. I hope you get how to determine or derive this equation of the response of a second order system in the underdamping case. Thank you.